Hello everybody, welcome to this brief video on affine projection as a dimensionality reduction technique and a bit of an introduction to principal component analysis, or PCA. So on the first day of classes, Professor Draper showed us the eigenfaces demonstration as an example of what we could do with some of what we learn in this course. And in this document, I am going to be reviewing the affine projection techniques we learned and connecting them to topics of dimensionality reduction, including the eigenfaces demo. So to begin, let's start with a particular distribution of data in three-dimensional space. So we have this important data set right here, and we have three values for each data point. And if we plot them out, they look something like this. So you have a bunch of these purple dots distributed kind of in a line in three-dimensional space. And so fortunately, we're able to pretty much perfectly form a line that goes directly through this distribution. And the distance from the points to this line is very small. And we'll recognize this line as a one-dimensional affine set in 3 dimensions. And so we can define that affine set through the use of this vector v0 and the vector x0. And so we say that this green line is the set of all x, such that x is equal to alpha times v0 plus x0, where alpha is in the real number set. And so if we were to tell our friend, okay, here is the value of x0 and here's the value of v0, I'm just going to tell you the alpha values, and that's how you're going to be able to tell what the location of these points are. Then I could actually just give my friend just one number, that alpha number, to communicate where all of these points are in 3D space. And so that is an example of dimensionality reduction. So I was able to reduce the dimensionality of the data from 3 dimensions to 1 dimension. Now, similarly, if we had data that was distributed in a 2-dimensional sort of fashion, we could also do a similar sort of procedure where we use a 2-dimensional affine set and we project the points onto that 2-dimensional set, and we just define the set using similar notation. We have x0, which is our offset vector, as well as v0 and v1. And so, yeah, we just have to tell our friend what the values of alpha 0 and alpha 1 are, and then they can reconstruct the position of these points in 3-dimensional space pretty accurately, and we only had to tell them 2 numbers. So that's an example of reducing the dimensionality from 3 to 2. So now let's think about a bit of a higher dimensionality example. So let's say that we have a set of faces. So this is basically the eigenfaces demo. So this image of a face can basically be broken down into a vector where each pixel is the value of the vector. So in this case, I have them from 0 to 1. So this I over here, I'll just circle it. The I over here has a very dark value, so x50 is 0, x0 has a very light value, so it's 0.9, and then 0.8, and so on, and then we have all the way up to x1000. So this is very high dimensionality data, and so the question is, can we actually find like a good affine sets to project our vectors onto that do a good job of maintaining the detail? So in the cases beforehand, we had this really convenient distribution of data, right? It's really close to this plane in 3D space in this case, and it's really close to this line in 3D space in this case. So how does that work when we expand to higher dimensions? And this is something that's kind of hard to get an intuitive sense of, but the answer, as it turns out, is yes, we can find some really, really good affine approximations for this kind of data, and that's literally what the eigenfaces are doing. And so basically, x0 would be the mean face, and then for all of the actual, components, or principal components they're called, each of these vi vectors, they would all be mutually orthogonal, and we would be trying to maximize the variance of the projection of each of these data points. So if we go here, we see that if we project these data points onto here, then this vector, this v0, does seem to maximize the variance of the projection values. So these are really spread out. And if I were to turn this v0 so that we're more like this, then I would actually have a smaller spread of the data. And you can sort of see that visually here. And so yeah, what we want to make sure of is that each of these values are, or each of these vectors are mutually orthogonal, and that they maximize the variance of the projected data points. And so I won't be going into the full derivation of this, but basically the way that you can get those in a very quick way that doesn't require iterative optimization of the variance of the projected points is to take the eigenvectors of the covariance matrix. So if we take the eigenvectors of this matrix, which is formed out of taking the covariance of each of these indices in these vectors. So yeah, you create that matrix, it's going to be an n by n matrix, and that if you take the eigenvalues, you'll actually get the perfect values of v1 through I guess vn, but you can select the first k, and those will give you a really good set of vectors to use in your principal component analysis so that you can make a good approximation of this face using only k vectors, where k is much less than n. And so, yeah, you can make these approximations for faces, which are pretty complicated data structures, and you don't need to have that many principal components to make a good approximation. And so then you can feed in these alpha values, these coefficients that you find just like we would have in class, just with more dimensions. You feed in these alpha values to, let's say a machine learning model. And since you have roughly the same amount of net information held about the nature of the face, you can have some really good results there where you don't have as much overfitting. You can train a model using a lot less data on a given face. But yeah, as it turns out, you can make these eigenvectors for images and faces, and they work really well in approximating those in a very condensed manner. I hope you've enjoyed this video on affine projection as a dimensionality reduction technique and this sort of introduction, a soft introduction to principal component analysis. And yeah, thank you. I hope to follow up on this discussion if you guys have any questions.